pre-learning about the ideal gas equation. You will need to make notes during this. So we should know that gases, the particles in gases move fast, they're constantly moving, they're colliding with each other and the sides of the container, and they occupy a large volume. So when we're talking about the ideal gas equation, we need to make some assumptions. So the assumptions we make are as follows. You should stop the video now and note down these. Most of these assumptions are absolutely fine, okay? But there are two assumptions which we make which are actually physically completely wrong, and we should know that they're wrong. So one of them is that there are no intermolecular forces between the molecules. Now, you'll learn this about intermolecular forces, or you should know from GCSE, that there will be forces between molecules. The other one is that the volume occupied by the molecules themselves is entirely negligible. Well, atoms do take up some volume, so that's not quite right either. However, even though we have gases which are clearly not going to be ideal gases, we can still use the equation to give a very good approximation to work out various things about the gas. So the thing you need to know about the ideal gas equation is the expression PV equals nRT, where P equals pressure of the gas, V equals volume, N equals number of moles, R is a constant, the gas constant, and T is a temperature. And furthermore, you should know that pressure must be measured in pascals, volume in meters cubed, number of moles is just a number, R, the constant, is 8.314, which you will be given in the exam, and T is the temperature in Kelvin. So, as I said, P must be in pascals. Now, often, to make the numbers slightly easier, we use kilopascals. You might rarely come across some units called atmospheres, where 1 atmosphere is 101.325 kilopascals, or a bar, which equals 100 kilopascals. Volume must be in meters cubed. So, 1 meters cubed is a meter by a meter by a meter. Now, I think of that as a pretty decent Christmas present. 1 decimeter cubed is 1 decimeter by 1 decimeter by 1 decimeter. So that's 1/10 of a meter in all directions. Now that used to be the size of an innocent smoothie. The other unit, you know, is a centimeter cubed. So 1 centimeter by 1 centimeter by 1 centimeter, a sugar lump. Now you should be able to scale these up. So if you were to take a sugar lump, 1,000 sugar lumps would be contained in an innocent smoothie. And you could get 1,000 innocent smoothies into a pretty big box. So that's how you have to scale them up. You need to realize that there's a 1,000 factor between each of these. Now, N is the number of moles, which you sometimes need to make a calculation to get. And R is the gas constant. It's 8.314 joules per Kelvin per mole. Don't worry too much about the units. And finally, temperature. So temperature must be in Kelvin. Now, Kelvin is a centigrade scale, which means between the freezing point of water and the boiling point of water, there are 100 units. But 0 degrees C is equivalent to 273 Kelvin. So if you are given a temperature in degrees C, you need to add 273 to your number. So let's have a look at a quick example. We want to calculate the volume of 1 mole of gas at 100 kilopascals and 25 degrees C. So what you would need to do, PV equals nRT. We rearrange to make V the subject of that equation, nRT over P, and then we put the numbers in. 1 for the number of moles, 8.314 for the gas constant, T, now 25 degrees C plus 275 gives 298 Kelvin, and divided by P, the pressure in pascals. So 100 kPa is 100,000 pascals. Now that gets you 0.0248 meters cubed on your calculator. Now, if you turn that into decimeter cubed, that becomes 24.8 decimeter cubed, which is not too far away from what you needed to know at GCSE, that 1 mole of gas at room temperature occupies 24 dm cubed.